Hello everyone. Today we'll see one of the critical aspects of modern day processor, that is branches, and why it is absolutely critical to predict whether the branch will be taken or not taken. Now if we see this code, the part inside the if loop, whether this will be executed or not depends on the value of x. Now when it is translated into an assembly level code, it comes something like this, and the final value of PC depends on the value of these two registers. Now, if both of them are equal, it will take the value of label, and if they are not equal, it will increment the PC. Now we'll see how these branches affect our pipeline. So if we consider a standard five-stage pipeline with fetch, decode, ALU, memory, and write back stage. Now in the third stage, we resolve a branch, and by then only we can know whether the branch is taken or not. But by then we have already loaded two more instructions in the pipeline. And if the branch is taken, then we need to flush out these two instructions and load I3 and I4, which is at the label. So this leads to increasing the CPI of the pipeline from the ideal CPI value of 1. So if we see a stalled CPI, this means the CPI of a stalled pipeline. This is 1 plus whatever penalty we are paying per instruction. Now this penalty per instruction can be divided into two parts. How much penalty we are paying per misprediction and how many mispredictions we are doing per instruction. Now the first part is a function of the predictor, how correct you are able to predict. And the second part is the function of pipeline. The deeper the pipeline, the more penalty you pay during misprediction. As you can see here, this pipeline resolves the branch here, and there is a penalty of 40 instructions, which is too huge. So we'll try to improve this predictor only so that we can predict correctly and we can reduce the number of mispredictions so that the CPI can be closer to 1. So essentially we just need the value of PC at every instruction. So whenever we get an instruction, if it is a non-branch instruction or a not taken branch, we will increment the PC. And if it is a taken branch, we'll take the PC value from the label. So how to get the next PC value? For that, we use a branch target buffer, which indexes itself using the current PC and gives us the next PC as the output. So now we'll see some implementation of branch predictors. So we'll first of all we'll see a 1-bit predictor, which is also called a direction predictor. It maintains a BHT, also known as a branch history table. So each value, each index can have two values, 0 or 1. If it is 0, that means it's a not taken branch and you can increment the PC. And if it is 1, it means it's a taken branch and you have to go to BTB or the branch target buffer to know what is the PC value. But when we see it for this sequence, then this sequence has one anomaly, and because of this one anomaly, this will move to a not taken stage. And when we get a taken just after this, still it will be not taken stage, and then it will move to taken stage. So both of this we are mispredicting. So for one anomaly, we have two mispredictions, which is a problem. So to resolve this, we'll try to add one more bit and create a 2-bit predictor. So this bit, this is essentially a hysteresis bit, which controls what kind of not taken or taken stage you are in. So if we see a finite state machine implementation of this, so 0, 0 is a strongly not taken stage and 1, 1 is a strongly taken stage. So if you are in a strongly not taken stage and you get a taken value, you are still in a not taken stage, but it is a weak stage. And if you get one more taken, you will move to a weak taken stage. So if we see the same sequence of events here with one anomaly, then we see that from the start, the branch is in a strong taken stage until it hits the not taken value. Here the branch moves into a weak taken stage and gives a misprediction. But after this, if we have a taken, the branch starts to predict correctly. So essentially, we just get one misprediction, which resolved our previous issue. So this branch predictor is actually very good at predicting. It predicts around 90% correctly for the branches we have, and it is very commonly used for the modern day processors.